Now let's really examine this problem, and let's have a look at the problem definition. This is a sheet metal forming problem, and this is a sketch of the problem, an idealized sketch. In reality, however, we don't have a sharp point load, neither do we have sharp corners for the base. So in the real lab, we would have a rounded loading tip and corners with fillets. And let's see if we model the problem as an experimentalist and try to include these curved loading tips and fillets, and see if they can improve on our convergence. Now we are here at 0.17 step time. Let's modify the model. Let's copy the model to model 2. Now let's go to the part. So since now we need to model the round loading tip, we have to create a separate part. So we first create the new part, which is the indenter. 2D also we make a deformable, and then as we've done with the base, we change it to rigid later. So for this, we can consider it as a rounded loading tip. So we can simply create something like a rectangle, and then we use a fillet. Here we need to fill in the fillet radius. So ideally we want to use something different, but smaller maybe. But we can try with 2 first to see how it works. See if it improves, and then so we first click on the entity near the end to be filleted, and then we click here. Here we have a radius. Also we need to modify the geometry, create some constraints, dimensions. The radius is 2, we can make this one also 2. So this left is edge is the symmetric part of it. Click done. So we have our loading tip. Now in a circle, an arc. And we, as usual, we allocate a section. We have the section already defined, we can reuse it. We create a mesh. Here, the mesh that matters is the point where it comes into contact. We want to use a final mesh. We could use 4. Let's start with 4. And then we mesh it. For this one, element type doesn't matter, so we just mesh the part. And it creates such a irregular part. So of course we can change the element type. Mesh control, we can make it to be triangle. More uniform. Okay, let's stick to this one. Now we've meshed our indenter, and we need to modify our base, because here we have sharp corners and we want to reduce, make it smooth. So we go to section sketch. Okay, we create a fillet. Again, radius 2. Click here, here. Now we have the radius defined. Done. We need to regenerate the feature. Go to part, and the feature we click regenerate, and now we have our newly defined geometry. Of course, here now we need to remesh it. Again, this is the edge that would become important. We apply 4 as a start, mesh it. This looks okay. So this is the rigid body, so the mesh doesn't matter that much. One thing important is that we need to redefine our surface, because now we need to include this fillet region in the surface definition. And in the indenter, we also need to create a surface. This would be the bottom surface. Select this part, because this is the part that is actually going to come into contact with the plate. And now the plate needs to include 2 surfaces, one on top and one on bottom. So previously we only have the bottom, now we also need to include the top, which comes into contact with the indenter. So we have defined all the surfaces, and we've recreated the geometry and the mesh. What we should do is to modify the general contact. Okay, here it does not allow us to modify it. Still does not allow us to modify it. What we can do is to simply delete it and regenerate. General contact. Select surface pairs. We have the base top in contact with the bottom of plate. We have so no wonder, yes, cancel, because we haven't put the part in assembly yet. Right, so we need to put the indenter in, apply, and then we need to shift the indenter. Translate. Starting point here, ending point here, and now we are okay. So now this point is going to push down. Okay, we redefine our interaction. Initial general contact. Alright, now we should have all the surfaces. Yes, the base, top of the base with the bottom of the plate, and then bottom of the indenter with the top of the plate. Okay, contact property defined. We've defined our interaction. Now we need to create the rigid body, so it should be under constraint, but before that we need to create the reference point. So here we create a new reference point for this rigid body. Click it here, reference point 2, and then we create the constraint rigid body for the indenter. Select the body, click on the body, select the body, and then the reference point is reference point 2, click OK. So now we have defined our indenter, so we need to modify the loading such that the load applies on the indenter instead of on the tip of our plate here. So here we go under boundary condition, we modify our load first. Region would be the whole indenter. This is the rigid body, so we just click the body. We could also apply directly on a reference point. It serves the same purpose. Now we need to include the symmetric boundary condition, modify the symmetric boundary condition to include the left edge of the indenter. Edit, clicked. Now we are in the loading. Okay, so we need to go to the initial step, because that's where we define our symmetric boundary condition. Now we can modify it. Hold shift and select the left, and click done. And yes, now we have modified our symmetric boundary condition as well. So contact defined, mesh defined, boundary conditions modified, we need to go to the last step, unloading, and we need to check that, okay, node is still inactive. So that's for the elastic spring back part. Okay, so we can try again. Create a new job. Track PC5 trial 2. And think about it again. Okay, this time is much better. We run into 0.56 and increment 100. So let's have a look at the error message, because I suspect that this is because we run out of increments. Yes, too many increments needed. Indeed, this is not yet a convergence issue, so we go to loading. We increase our increments. Let's be a little bit braver. So now we have 10,000 increments, should be sufficient. And we have completed the job. Result. Yes, so now we run into full increment, and you can see that it bends quite a lot downwards, and we can have a look at our plastic strain. Equivalent plastic strain is at 0.4. This is a lot, and we can have a zoomed view of what's going on here. You can see that one thing to note is a contact. Let's have a look at the contact pressure. Yeah, so here it's not very well shown, but this looks like all blue. Yes, or zero. This is because we are in the elastic spring back. Because of the unloading, there is a small elastic deformation pushing up our indenter. And at the end of our unloading, all the contact pressure becomes zero, which makes perfect sense. And at the beginning of our unloading, at the start of it, the contact pressure seems to be concentrated here, and there seems to be no contact here. Could be the case, but could also be the fact that we have a rather coarse mesh here compared to the radius of our contact. And you can try improving on the mesh to see how whether your results change. One thing I would like to check is to calculate the angle. So we can check if the angle is 90 or not. And for this, what we can do is to calculate this angle. So we calculate the distance between this node, for instance, and this node. This, under the deformation scale of 1, we have the distance in x direction, distance in y, and the total distance. If we want to have a in total 90 degree, our distance in x and y, they should be the same. But it clearly that the distance in x and y between the two nodes, they are quite different. In fact, our y direction distance is 1.731, which is much larger than the x direction, which means that we pushed it a little bit too far. You can modify your indentation depth, taking into account that the curvature would reduce the actual level that's needed to create a 90 degree angle, and play around and then come up with the optimal distance of indentation, such that eventually you, after the spring back, you get a perfect 90 degree angle. So this will be an interesting study, so that you don't have to repeat a lot of experiments and You do the simulation and then you validate eventually on actual experiment.